we'll get through this part pretty handily, I think. So matter is made up of atoms. It has mass and occupies space. This is actually unit 1 thing where we say it could be a mixture or it could be a pure substance. Oops, goodness. Okay, so if it's a mixture, starts with the letter H, what 2 types of mixtures do we have?
Homogeneous and heterogeneous.
Yep, homogeneous and heterogeneous. Okay, so if it's a pure substance, what are our options?
Element and compound.
Yep, element and compound, CPD for compound. Yep, and that's kind of where we're picking up today. Now, this is actually unit 1 too. We said that an element is all the same atom, or say an element, all the atoms are the same. So if you have a chunk of copper, they're all copper atoms. Chunk of carbon, they're all carbon atoms. One of the things about the elements, we said you can use the periodic table, and I call it the decimal number. We'll pick on carbon. The decimal number for carbon is 12.01. Okay, and we said that does double duty. We said that's how much a carbon atom weighs. 12.01 AMUs is how much one carbon atom weighs. And when we also said 1 mole of carbon will weigh 12.01 grams, right? That's like the molar mass approach. Well, we're going to take it up now to compounds instead of elements. The cool thing about compounds, obviously, is you have a formula that represents the repeating unit of a compound. A lot of these slides are like repeat slides. I'm like, that's a deja vu slide. I swear, it's a deja vu slide. Okay, compounds. They're made up of 1 type of repeating unit. I'm actually going to go ahead and add, I'm going to take my compound and I'm going to put it over here. And I think I talked about this before. There are 2 types of compounds. There are, let's start with molecular CPD, and then there are ionic CPD, okay? We'll be talking more about compounds, but just to kind of remind you. I mentioned this because right off the bat, the repeating unit of a molecular compound, we're going to call that a molecule. And for an ionic compound, we're going to call that repeating unit a formula unit. Otherwise abbreviated FU. Really, I'm serious. Formula unit. You see where you get FU from that? Anyway, I just think that's funny. It's probably not very mature. But an example of a molecular compound is cute little water molecules. An example of an ionic compound is table salt. All right. So that's why the compound, there's 2 types of compounds. Molecular, oh goodness, and ionic. All right. Oops. Okay. So the thing about a compound like water is we could take the, water is H2O, so we have an oxygen, chemical bond hydrogen, chemical bond hydrogen. We could go ahead and take some energy and break that chemical bond, and we could break it down into a pile of hydrogen, pile of oxygen. Totally good. What ordinary means. So the other thing about a compound is that those diatomic elements, the Hoffer-Nichols, the H2, the O2, the F2, those are not compounds. They are molecules, but a compound needs to have two different elements that are combined together. This actually is something I think we looked at before. Mercury 2 oxide is this right here, and actually it's a solid, and we are applying heat here to break the mercury 2 and the oxygen bonds, and here we got leftover liquid mercury, and we couldn't see it, but actually there's a video. We could see those little O2 molecules scooting away. So this is a chemical reaction. We have something different in the end than we started with. Mercury 2 oxide would be a compound. Okay. Formula for mercury 2 oxide is HgO. These are all formulas of compounds. Okay. I'm going to go ahead and add something to my my molecular compound, ionic compound. And again, we'll be hitting this later too. But for an ionic compound is look for the metal. Has a metal somewhere in there. Okay. No metals in general. Along those lines, I'm going to consider hydrogen is equal to non-metal. So here we go. Got some formulas of some compounds. How do I know where the metals are on the periodic table?
The thing, I don't remember what you called it.
I call it a JAG. The stair steps or the JAG. Yep, exactly. So these, what are these? Metals. Yep, and these little small things are non-metals. Of course, we have the metalloids kind of along the stair step. So metals here. So bottom, and I said for purposes of identifying whether it's molecular or ionic, hydrogen is a non-metal. So here we have, and don't feel shy about looking at the periodic table. So hydrogen's a non-metal and oxygen's a non-metal. So water has two non-metals. So actually it's a molecular compound, just like I said. I told you NaCl is a ionic compound. So which one's the metal, the Na or the Cl? Yep, the Na, that's the metal, yep. So along those lines, as I'm kind of looking down here, kind of blares out at me, is calcium is a metal. Well, we'll talk about how do you name these things, but actually I would draw a line right here after the calcium before the SO4, and this is what we call calcium sulfate. So this must be sulfate, eh? Ammonium sulfide. This is ammonium, and the S here is not sulfite, actually, because it's, we'll get into it, but it's sulfide. This is actually an exception to this rule over here. This is an ionic compound. Magnesium NO3 is nitrate, magnesium nitrate. Is that ionic or molecular? It is ionic. Why is that? Because the magnesium is metal, yep, exactly. But my point in this context of what we're trying to learn today has nothing to do with ionic and molecular. We just need to kind of get past the concept of a compound. We use formulas to represent compounds. Okay. So I kind of already said this, already started kind of saying compounds. We use formulas to represent compounds. Options for compounds are molecular compound or an ionic compound. I'll go ahead and put one more thing up here. Under molecular, because you might hear me lapse into it, a synonym for molecular compound is a covalent compound. Covalent, CPD, they mean the same thing. So I'm going to try to kind of, and I might have gone through this in Unit 1, I'm not sure, try to describe why, as that first thing says, why do we call a repeating unit a molecular compound a cute little molecule? It's kind of isolated molecule, and versus the repeating unit or formula unit if it's an ionic compound. And here we go. These are all molecular compounds. Now, if you're like me, you might be, what's up with the little line with the two dots? Well, you might remember that from your days gone by, but those are actually lone pair electrons. We'll be talking more about that. But bottom line, methane, CH4, you see the carbon in the middle and the 4 hydrogens. Ammonia, NH3, you see the nitrogen in the middle, 33 hydrogens, 1 lone pair electron. Water, H2O, we have the red oxygen here and the 2 hydrogens, 2 lone pair electrons. Think about lone pair electrons as they give shape to the molecule. So that is definitely a player. Methane, CH4, there's different ways to kind of look at what that would look like, okay? There's just the straight old formula, and then this is just a, what do we have here? Structural formula, that's B. C is a ball and stick model, and D is a space filling model for all methane. This is benzene, C6 H6. Again, kind of the different representations. Here's a picture under normal temperatures on Earth and pressures on Earth. Benzene's a liquid. This is vinegar. So the formula for vinegar would have 2 carbons, 4 hydrogens, and 2 oxygens, which isn't really very descriptive of what vinegar would look like. Here's how those atoms would be arranged, and here's the visual representation. But again, it's a repeating unit. We know what the formula is. Molecular compound, another molecular compound, acetic acid. Oh, that's kind of vinegar. Same thing. Vinegar, acetic acid, same thing. Methyl formate. I think the point here is they both have the same formula, but what's different between the two? The structure's different. And it's kind of like you play those games where what's different with these pictures? Here we have a hydroxyl group. We'll talk more about that later. OH is hydroxyl. And here we have kind of, let's say an ester, I'm not sure, where the oxygen is brought in and then the hydrogen is right there. But they behave, these are different cats, the same formula, but they behave differently. So molecular compounds won't have a metal. Molecular compounds, no metal. And we talk about the repeating unit as a molecule. And it's kind of like if you go to a magic show and the magician makes their assistant hover, and what the magician will do is kind of go like this with their, say, see, she's not, I don't have any strings, I don't know how they do that, I'm not here to explain that. But to me, that's like a molecule. It's not really connected to anything. Okay, so we call that an independent molecule. Now, switching gears, I told you H2O is an example of a molecular compound. NaCl is an example of an anionic compound. So I think we watched this before, we'll probably watch it again, but one of the things about metals is they're good about losing electrons. So if I were to watch this video, you were going to actually see an electron go from the metal to the non-metal, and in doing so, it becomes positively charged because it lost an electron. We've talked about that. The chlorine becomes negatively charged because it picked up an electron. And then we have a dot, 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 dot. That dot, 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 dot is a chemical bond, but it's an ionic chemical bond. And it's just because we have a positive over here and negative over here, and they have attraction for each other. Okay. So, I don't think this video played because I didn't hot link it. But this is a bromine compound, and they form these crystalline lattice structures. Let me show you. So this is salt. This is NaCl. I told you that the sodium will kick off an electron, become plus, specifically 1 electron, so it's +1. The chlorines pick up 1 electron, become a -1. So we have these alternating kind of little sort of situation where you have positively charged cations being attracted to negatively charged anions. So this is actually what we call crystalline lattice. So under ionic compounds, they form crystalline lattice structures. So the reason you can't really, like the magician couldn't take his wand and kind of go all the way around is because he would run into a chemical bond. Okay, so this is a crystalline lattice. In their solid state anyway. So it's not to say that we couldn't grab a repeating unit here. We could grab a repeating unit here. We could grab a repeating unit here. Okay, we could grab a repeating unit here. So you just kind of have to grab and go, but they're all connected in their solid state. This is just another look at kind of the crystalline lattice structure of a solid ionic compound, in this case sodium chloride. So the way this crystalline lattice structure works is for every cation you have 6 anions connected to it. For every anion you have 6 cations connected to it. That's just the way it works. Formula unit. Okay. And I kind of already said this before. In general, if you look at the formula of a compound, you'll look for the metal. If it has a metal, it's ionic. No metal, it's molecular. The metal makes it ionic. Okay? And the reason the metal makes it ionic is what I just explained about sodium chloride a minute ago. Metals are great at wanting to give up electrons. Okay, so we form that ionic chemical bond. So this is all to get us to the meat of today's lecture. These last few slides are kind of where it's at. I kind of set the stage with compounds. Here's the deal. These are pretty straightforward. We know that for the elements, if we want to know how much an atom of a particular type of element weighs, we just go to the periodic table and grab what I call the decimal number, okay, and that's how much it weighs in AMUs. So if you want to know how much a molecule weighs, you better have a periodic table handy. All you got to do is add them up. That's it. That's totally it. So molecular weight, how much a molecule weighs, we call it molecular mass. But do you see why we have two different things now? Molecular weight, and the other one is formula weight. So before I do that, let's pick on something that's a molecule. Structure of aspirin, the repeating unit, has 9 carbons, 8 hydrogens, and 4 oxygens. So guess what? If you want to know how much a molecule of aspirin weighs, we go to the periodic table, we find the decimal number for carbon, we take it times 9. We find the decimal number for hydrogen, we take it times 8. We find the decimal number for oxygen, we take it times 4. That's it. We add them all up. Now, the thing about rounding is, how does this work? These numbers are exact. The 9, 8, and 4 are exact. You probably buy that. They bring no uncertainty. There is uncertainty in these numbers that we got from the periodic table. So, bottom line is, no uncertainty is brought as we take the exact number times an uncertain number. So these are relatively exact, this last column. So now the last thing we're going to do is add up what's brought by the carbon, what's brought by the hydrogen, what's brought by the oxygen. We're adding. We don't add much in chemistry. And once we add, we round according to decimals. So we're going to actually, even though we have 3 decimal places there, we're only allowed 2 decimals. Okay. After you do, you guys will, if you haven't already done a lot of these, you guys will be doing these in your sleep. What's the molecular weight of aspirin? And basically, if you're dealing with something that's heavy, anything heavier than, goodness, anything heavier than 10. So, beginning boron and all that. Okay, if that's in your formula, you're going to only have 2 sig figs. Okay, if you only have lithium, beryllium, helium, or hydrogen, it's probably going to, I said sig figs, sorry, 2 decimals. You'll have 2 decimals. If you have something light, it'll be 3 decimals. Don't forget when you're doing a simple problem like this, a few things, show all your work. Be like, oh, Mrs. Snipes, you have a periodic table. You know what I multiplied together. I'm like, no, that doesn't work that way. Show all your work and include units. Okay. So, molecular weight is what we calculate for molecules, and it just sounds almost downright silly to say formula weight is what we calculate for ionic compounds. I'll put MW for molecular weight, and this is FW for formula weight. Why? Because we have formula units here. Why? Because we have molecules here. So it's a little bit of semantics. It's done the same way. All right, so if we pick on sodium chloride, we have 1 sodium, take 1 times the decimal number for sodium. We have 1 chlorine, 1 times the decimal number for chlorine. I think chlorine is pretty cool because it's 35.45. How did that work? Okay, and then sum those 2 columns. Again, get in the habit of showing all of your work and include units. Now the units are kind of built into, it's kind of weird how units are. I wouldn't like it. Units are built into this column, but they should also say subtotal AMUs there. Okay? So I'm going to do a couple of examples, and then that's what your homework is going to be. So hydrazine, we have 2 nitrogens, 4 hydrogens. I told you hydrogen is a nonmetal. Nitrogen's also a nonmetal. Since there's no metals there, we're looking at a molecular compound. So we're going to knock out the molecular weight. That's kind of how that goes. So I'm going to take 2 times 14.01 AMUs, that's for the nitrogen, plus 4 times 1.008 AMUs, that's for the hydrogen. And like I tried to maybe kind of convince you, if you're having something that's got any heft to it at all, you're probably in this sort of problem only going to be allowed 2 decimals, not 2 sig figs, 2 decimals. Okay. Now, honestly, when I get to working these sort of problems, like on homework or for a test, I will probably say something like this. I'll probably say MW of N2H4, and then I probably wouldn't include these AMUs in working the problem, but I would definitely include the AMUs in the answer. So just so we're all on the same page there. So that's for the molecular weight. Let's do a formula weight. Calcium nitrate. How many nitrogen atoms do I need to account for here? 2. How many oxygen atoms? 6. Exactly. So here we go. 1 times 40.08 plus 2 times 14.01 plus 6 times 16.00. Another thing I've seen, or one of the things I've seen students sometimes is, and I can see why, we do a lot with oxygen in chemistry, or our chemistry anyway. They will say, why do I have to put those extra zeros? Why not just go with 16? And because if you just put 16, it says 16.00, honestly, when you do your final result, you should only allow yourself 0 decimals, because that was one of the terms that had 0 decimals in it. 16.00 is a different number than 16. Any questions about that? So you get 164.10 AMUs. See, I told you it's not a mind bender. There are certain things in chemistry that are mind benders. This one's not. Okay. That's as far as I wanted to get today. On Wednesday, though, we will go into part 2. So it should be fine too. That leaves you time to do those problems at the end of lecture. Got it. You're at the end of part 1. Sometimes if you have questions about the problems, you can